This video covers only questions 7A and 7B. Question 7A is just how to differentiate EMF and PD, and question 7B is an application of Kirchhoff's first and second laws. Before going over question 7A, I'm going to show you a couple things related to a battery or cell. This is a D battery, and here is showing the voltage is 1.5 volts. This is a AA or double A battery, and this is the voltage 1.5 volts. On both batteries with cylindrical shape, the polarity is showing here. So we have the polarity positive and negative on the other side. This is another alternative for batteries where the terminals are just on one side. And this is the positive and this is the negative because it's indicating here. And this is the voltage is 9 volts. All batteries in the market, they show the polarity, positive and negative. And also, they have a different shape and size, depends on the application and how much energy will be drawn from the battery. So the principle of the battery, they have a chemical composition inside of each battery that is going to transform the chemical energy into electrical energy by moving electrons from one side to the other side of the battery. So this is the definition for EMF, abbreviation for electric motor force. Transfers chemical energy to electrical energy. This is a resistor and this is a light bulb. Both components in an electric circuit need a battery to provide the energy in order for those components to work. So this resistor, when connecting a circuit, is not going to give any sign of current passing through, but by touching we can feel it's a little bit warmer. Now this light bulb is going to produce light because the energy provided by the battery that is flowing through the light bulb. So both components, they are going to use the energy provided to produce different types of energy. So this is the concept of PD, or potential difference. Transfers electrical energy to other forms of energy like heat and light. So that's the main difference between EMF and PD. Next, we have this diagram that's showing two EMFs, E1 and E2, and 3 resistors, R1, R2, and R3, and they are connected as showing. I'm going to replace all those components of the circuits with real ones, like this. So here we have 3 resistors. We have the battery with the polarity positive on this side because that's the longer line, and we have the currents with directions that was provided by this picture. So in this picture we have a couple things that we need to look at. Is the term with reference letters A, B, C, D, and also in the center X and Y. And we are going to divide the circuit into loops to verify how can we apply Kirchhoff's laws. So the first question is using Kirchhoff's first law to write down the expression relating all the currents in the circuit, I1, I2, and I3. Kirchhoff's first law states that the sum of all currents entering any point is equal to the sum of all currents leaving that same point. This law represents the conservation of charge. In this point Y, we are going to apply Kirchhoff's first law, which states that the sum of all currents in is equal to the sum of currents out. So the currents in is just I3, following the direction given by the problem. And currents out, we have I1 and I2. We just need to add them. So here we have an expression for that relate all three currents. Now let's apply the same on this point X, or joint. Here we have currents in is I1 plus I2, and current out is I3. So this expression that relate all three currents, they are exactly the same. The answer for this question is I3 is equal I1 plus I2. The next question is asking to use Kirchhoff's second law to write down an expression related to all the components of the circuit in the loop X, B, C, Y, and X. So the loop is X, B, B, C, C, Y, and Y, X. Kirchhoff's second law states that the sum of all the EMFs around a closed loop is equal to the sum of all PDs in the same loop. This law represents the conservation of energy. So here is a simplified version of Kirchhoff's second law. The sum of all the EMFs is equal to the sum of all PDs in the same loop. The first step in this problem is to determine the direction of the loop. In this case, I like to use the battery polarity to guide me with this. Since this is positive, so I like to follow the positive sign. So my loop direction will be like this, from negative to positive of my battery. So before arranging all the EMFs and PDs in this equation, you need to determine direction of a loop. It's completely arbitrary. My preference is going from negative to positive of one battery that I have here, in this case just this. So go from negative to positive, so that's the direction of my loop. Now I look at this green loop, and the only EMF that I have is E2. So E2 is equal to, now I'm going to determine my PD. So the PDs is the resistance times the current, which is exactly voltage. So voltage, PD is the same thing. Okay, so now my resistance here is R2, and my current is I2. And it's positive because it's the same direction of my loop. So the current and the direction of my loop are the same. So this is positive. Now let's take a look on the next one. The next one, I have my R2. So R3, I3. and I look at the direction of the current that is flowing through this resistor. So the direction of the current and the direction of my loop are the same, so this is positive. So to answer this question, a expression relating all the components in this loop would be E2 equal R2 I2 plus R3 I3. The second question is asking to find an expression for the loop AXYDA. AX Y D A. So now I have this orange loop. So this is the expression for the green loop. Now let's find an expression for the orange loop. So following the same equation, the sum of all EMFs, so I have two. So I have to do E1 and E2, but I don't know if I should do plus or minus here. This is going to be determined by the direction of my loop. So let's say that I'm going to keep the same like this. So, and then I look where I am going over here. So it will be negative, positive. So this to me is a positive one. And then come this way, and now it's positive, and the next one is negative. It's the opposite of this. This was from negative to positive. I call my EMF positive. But now it's from positive to negative. So I'm going to change the sign. Now let's look the PD signs, the PD side of the equation. So I have here my R2 and my R1. So I'm gonna go ahead and write down R2 is being, the current is I2 right here, I2, R2. And the next one is R1. And the current that's flowing through these is I1. Remember, when currents, they cross a joint like this, they split. So it's not the same value of current that is flowing here. It's a good idea to place the current with the direction by the resistor so we can compare the direction of the current with the direction of your loop. So in this case, the current I1 that is flowing through R1 is to the left. So I place right here so it's easy for me, don't get confused about the direction. And I2 is flowing from R2 in this direction to the left. So both are flowing to the left. However, in this right here, my loop is flowing to the right at this time. So it's flowing to the right, the current is flowing to the right. So R1 times I1, which is the PD, is positive. Now my R2, my current 2 has the opposite direction of my loop. So in this case, you'll be negative. So you need to be careful with the direction of the loop that you are going to decide which direction you want, and how you are flowing with the negative and positive of the EMFs, and with the direction of the current that is flowing through the resistor. Okay, so now we can rewrite all this equation. Is E1 minus E2 is equal to I1 R1 I1 minus R2 I2. The order of the current and the resistor is not, doesn't matter. You could write instead of R2 I2 I2 R2. Will not matter, okay? Is optional. So that is the expression that using Kirchhoff's second law, we can combine all the components of the circuit.